Okay, our next talk is on some differential testing work from Rajdeep and colleagues at NUS. So please join me in welcoming them.
Hi everyone, my name is Rajdeep and today I'll be presenting our work on the mistaken assumption of interchangeable deep reinforcement learning implementations. So these are the contributions of our work. Firstly, we conducted a systematic and reproducible literature review that justifies the notion of researchers assuming interchangeable deep reinforcement learning implementations. Secondly, we proposed the differential testing methodology for comparing DRL implementations. Thirdly, we conducted large-scale experiments that showed that the implementations were indeed not interchangeable. Lastly, we demonstrated that this assumption was then significant enough to potentially alter or flip experiment outcomes. So recently, there's been an abundance of deep reinforcement learning libraries. For example, the library by Tianshou, by Dopamine, or by Stable Baselines Tree. And we've also noticed this trend whereby researchers assume that an algorithm will perform equally well across its many implementations. For example, the PPO algorithm by OpenAI Baselines, this is assumption that it will perform equally well with the PPO implementation by Tianshou or by Stable Baselines Tree. So we conducted a literature review to then properly justify this assumption. So we used Paper Copilot to automatically download accepted papers from top AI conferences, for example, NeurIPS and ICML. And we further filtered through these papers using PDF Plumber to then scope into the reinforcement learning papers, which reference at least 2 or more deep reinforcement libraries in their work. And after a manual inspection phase, we actually saw that 23 papers assume this notion of interchangeability, whereby they use an implementation of an algorithm which was not of the original implementation, thereby assuming that the implementations were interchangeable. So therein lies the crux of the problem, is because deep reinforcement learning is a complex domain, as seen in the figure on the right. It's actually the intersection between learning and reinforcement learning. So deep reinforcement learning inherently inherits hyperparameters for both domains. So there are many hyperparameters and there are many ways you can actually go wrong. So there's a higher likelihood of inconsistencies and mistakes. So for example, seemingly minor code level optimizations that can inadvertently have a significant impact outcome. So the question has to be asked, are the implementations of the same algorithm really interchangeable? So we actually conducted a pilot study to assess the potential for inconsistencies amongst different DQN implementations. So we tested 5 DQN implementations across 3 environments from the Atari benchmark suite, so using boxing, freeway, and Pong environments. And for each implementation environment permutation, we actually conducted 5 trials each, which is why you see shaded regions, which actually show the minimum and maximum of the trials. And the middle part shows actually the mean. So right off the bat, we can see, so for more context, the baseline for this experiment was Dopamine's implementation of the DQN algorithm, because there were some setup issues with the original DQN implementation, and the original author subsequently vouched for Dopamine's implementation as an accurate alternative in a GitHub issue. So we use Dopamine as the baseline. And from what we can see right off the bat from Dopamine's implementation is that it achieves very narrow margins between the minimum and maximum of its trials. Dopamine is the green line, and we can see that it achieves superhuman reward for across all environments. But this can't be said for the other implementations. For example, the implementation by RLib or the implementation by TF agents, we see that they actually achieve a wider variance amongst their trials, and some of them even achieve subhuman performance in some environments. For example, TF agents on the freeway environment. So to further investigate this, we actually crafted 3 research questions. The first research question is actually an extension of the pilot study we did with DQN implementations, but now we actually focused on PPO implementation instead. DQN and PPO are actually the 2 most frequently implemented algorithms by DRL libraries. So, but now we conducted our experiments on a larger scale. So instead of using 3 environments, we used 56 environments. And similarly, we tested 5 PPO implementations. So with 5 implementations and 56 environments and 5 trials, this leads to around 1.4K trained PPO agents to actually see if discrepancies are prevalent. And for the second research question, we then wanted to investigate why the discrepancies in RQ1 actually occurred. So we conducted a best effort debugging approach to inspect the source code and to figure out what was the root cause of the discrepancies observed in the first RQ. And for the last RQ, we then wanted to see if this assumption of interchangeable algorithms was actually sufficient enough to alter the outcomes of an experiment. So we replicated experiments from a study, but we used a different implementation of the algorithm the study used. And we wanted to see if just simply by using a different implementation of the algorithm, was it sufficient to actually change the outcomes of the study itself. So before I delve into the results of the research questions, for all three RQs, we actually adopted the differential testing methodology. So very briefly, given the same inputs, you then compare the outputs. But for a stochastic domain like deep reinforcement learning, this can't be done because given the same inputs, the outputs might not be the same. So we utilize stratified bootstrap confidence intervals proposed by Agrawal in NeurIPS 2021 to actually account for this. So given that you're testing an algorithm or an implementation across an environment suite, and you have multiple trials per environment, stratified bootstrap confidence intervals means that you actually sample from your result set multiple times, and then you can use an aggregation metric, for example, mean or number of trials with score more than some threshold to then get a distribution which properly estimates the performance of your algorithm. So this means that we can actually train on a large scale using minimum amount of trials. So typically you need 10 to 20 trials for accurate estimates. But then with bootstrap sampling, you can simply just train with 5 trials. So the results for RQ1, we can actually see that there are statistically significant discrepancies. So again, we tested 5 PPO implementations across 56 Atari environments with 5 trials each. And the x-axis represents the human normalized score over here, whereby if your score is more than 1, your agent is actually superhuman. And if your score is less than 1, your agent is subhuman. And the y-axis actually represents a fraction of trials with score more than the x-axis. So right off the bat, we can see that the different implementations can be partitioned into 2 groups. The first group we call the high-performing implementation consists of baselines, clean RL, and stable baselines tree. And the second group, which we call the low-performing implementations, consists of RLib and differential. So the high-performing group attains superhuman performance for at least 50% of their trials, whereas the low-performing group attains superhuman performance for only 15% of their trials. So we even scoped into a per environment overview, whereby for each environment, we investigated the training curves. And what we even saw discrepancies amongst the high-performing implementations themselves. For example, in the Analytics environment, we actually saw that the curves differed between the 3 high-performing implementations, where the curve by OpenAI baselines actually attained a mean reward of around 2 million, whereas the clean error and stable baseline tree implementations achieve a mean reward of around 1 million. So even among the high-performing implementations, there are discrepancies in some environments. So in RQ2, we actually investigated the source code to actually figure out what was the root cause of the inconsistencies. And we actually found multiple code level inconsistencies, but the primary inconsistency that caused the discrepancy observed in this slide was actually the number of frames per episode. So this was not correctly set for OpenAI baseline's PPO code. After setting it correctly to 108K as to what the other implementations did, we actually saw that the curves converged as expected. So for RQ3, we then wanted to see if this assumption of interchangeability was significant enough to potentially alter the outcomes of an experiment. So we replicated the experiments from a study which actually used the DDPG algorithm on the half cheetah environment to actually find the best hyperparameter values for certain hyperparameters. For example, the network architecture, the reward scale, or the batch size. So we replicated the experiments, but we used a different DDPG implementation instead. And we managed to actually change the outcomes of 2 out of 3 of the experiments. For example, the experiment on network architecture, the efficacy reported by the original study is shown in the dotted lines, and by ours is the solid lines. And we can see that originally reported was that the 400-300 network architecture actually attains the better mean reward, but our study showed that it was actually on par with the 100-100 architecture. For the reward scale, originally reported was that the no scaling, the scale of 1.0 was the best, but in our experiments, we actually saw that all 3 scaling factors achieve comparable results. So here are some key takeaways from our experiments. So researchers should actually exercise caution when using deep reinforcement learning implementations because your experiments can yield different outcomes depending on the implementation used. So you should not assume interchangeability. And discrepancies are most likely to be caused by code level inconsistencies. And we theorize that this is actually not intentional, but rather oversight stemming from a domain of high complexity. And lastly, using differential testing to actually identify these inconsistencies is actually simple and effective. And with reliable output estimation like certified bootstrap confidence intervals, it can be applied to other stochastic domains as well. So in conclusion, in our literature review, we've shown that multiple papers assume this notion of implementation interchangeability. And our experiments later showed that these implementations were not interchangeable, but rather unique. And this uniqueness that potential to flip experiment outcomes. So this warrants follow-up studies to test the claims of existing research under this assumption. This concludes my presentation. I thank everyone for attending and feel free to ask me any questions.
Thank you very much. Okay, we have time for questions. Okay.
So thank you for the presentation. Your hypothesis beyond for these differences that there are small technicalities in the implementation of the algorithms that turn the result to be different. Do you have any plan to validate this assumption or this hypothesis and go and see what are the actual differences that makes the result different? Maybe they are bugs or they are errors.
Yes, we actually found, for example, the curve by Tianzhe was actually the reason it was so low, it was because it was a inconsistent example in one of their code examples in their repository. So after we actually we actually went back and forth with Tianzhe and we figured out the reason. It was actually a code example which was wrong. And after that was fixed, the curves from our training converged. So, and then we did actually find some bugs. For example, in RLib, we tested with the SEC algorithm. I don't think it's currently fixed, but the bug was confirmed by the developers, whereby if you run the SEC algorithm with RLib on a discrete environment, it will critically fail. And to my current knowledge, it has not been fixed yet, but there was a bug. So we actually found multiple types of reasons for these inconsistencies. Some are bugs, some are because of the documentation itself.
Okay, thank you.
Yeah, kind of a follow-up to that gentleman's question. So, like, I understand you did a lot of work to find out these inconsistencies, but did you manage to categorize some of these inconsistent, maybe just slower to kind of find the actual optimal, but just slower to converge, or some of them just, not able to actually find as optimal solution as the other ones? Are you able to do that?
Yeah, so we managed to actually categorize the inconsistencies, and we actually saw that some inconsistencies were because of the API used. For example, if you use TensorFlow or PyTorch, gradient clipping might be slightly different, and this might account for inconsistencies as well. And with deep reinforcement learning, where you have a lot of hyperparameters, a single change might actually have a significant impact. So we did actually manage to categorize different inconsistencies in our paper. And if you would like to have no more information, you can actually read the paper. It's actually on arXiv. But we did manage to actually categorize, for example, API-based inconsistencies or actually logic-based inconsistencies as well, whereby the implementation itself is wrong. So for example, stable baselines tree and dopamine had different ways of decaying the E-value for the E-greedy policy. So the implementation of the E-greedy policy itself was logically different and not based on an API difference. So we did manage to actually figure out why this happened.
Right. Thank you very much again, Rajdeep.